Good morning, everybody. Welcome to the DeviceDojo. I'm Joseph, and this is where we tackle the practical side of securing connected devices, from over-the-air updates and fleet management to the broader challenges like incident detection and response, compliance, encryption, and more. Always actionable and hands-on, brought to you by Northern Tech, makers of Mendrayo. Let's get started. So, whoever's watching this, hopefully you woke up again. And today we're gonna just have a short session because I'm going to show you something which you hopefully are already using implicitly, and it just works and it helps. It's super simple. I want to talk to you about Fortify Source. So let me find the next slides. As I already told you, this is the DeviceDojo. My name is Joseph. This is being sponsored by Northern Tech. I work for Mendrayo. And the DeviceDojo is meant as content that is always actionable, that always helps you to make your devices better, more secure. That includes tutorials, also occasionally live coding, office hours, and in this case, a very little surprise for the next session. Yeah, hi, Michael. So, what are we talking about today? First, really short introduction into a very famous topic called buffer overflows. One more time. Then how these can be detected under some circumstances. Obviously, Fortify Source is one measure here. And last but not least, not one demo, two demos today, because I'm going to show you how this looks in code and how Yocto does things. And yeah, that's the plan for today. Let's get started with it. So, what is a buffer overflow? I assume that most of you have at least a little bit of knowledge about C/C++, mostly C in this case. So you know there's this dreaded thing called malloc, or variable declarations, where you create, allocate whatever, a string of a specific size. Usually, this is either a character pointer or a character array. It really doesn't matter in the end. What the compiler sees is an address of some storage. And by itself, it usually does not know how large the area is. As long as you take care to always use the same size and make sure that you do not go beyond these boundaries, no problem. No buffer overflow would ever happen. The problem is that if you pass those pointers around through the code, at the point where you use them, it's not always clear which size the storage area actually has. Because this is a very classic problem. At some point in time, maybe during initialization or of your application, you get a buffer. Or after some event like a network packet arrives, whatever. You allocate a buffer of a specific size. You do something with it. You move it around through the application. At some completely other point, there's, hey, I'm going to do something with this buffer. I'm emulating this here by a malloc in one function and sprintf, which would write to this very same buffer at a completely other point in time. If you look at these two lines of code, that's already a perfect buffer overflow because I allocate 10 bytes and then I write 12 plus 0 null terminator to it. Already broken, and it looks like whatever. The fun part is that this will actually probably pass the compiler and probably also not break the application, at least not right now. So what should we do about it? As I said, if this gets passed here, boom, a hidden boom might happen. Common library calls where this actually happens is, of course, memcopy, string catenation, string printf, memset, gets, whatever. Many of those also have a numeric parameter where you can pass how many bytes you actually have allocated. But if you don't know it, for sure, how do you make sure that you're not working on wrong assumptions about the size or the expected size of the buffer? That's what we're talking about today. So the first and simplest thing here is runtime detection, because technically, and that's what also a number of more modern languages do, is they memorize the size of the buffer, and whatever operations happen on it, they make sure that they do not exceed the end of the buffer. That's why what I'm saying here does not directly apply to Rust or Go or any of the new languages, unless you beat them heavily. But for C++ or C, how could you do it? The common tooling here is Valgrind. Valgrind is a toolset for memory profiling, debugging, all kinds of crazy stuff. I've used it extensively in the past. It is awesome. If it is not in your tool chest, please learn about it basically after I stop talking, okay? The most important thing about Valgrind is memcheck. I've linked the quick start here for you, and memcheck, or you can invoke Valgrind with memcheck on whatever executable you have. So taking my earlier example, as I said, character with size of 10, I'm printing to it, and hopefully you can see it. If not, zoom in later in the recording. If we run this in Valgrind and the invocation is on top of the screenshot, it will already tell you, hey, you're writing out of bounds here. Something is wrong. So if we could just use this all of the time, no problem, right? No more buffer overflows ever. The problem is Valgrind is only at runtime, so you might not even notice it during your development, and it has extremely high overhead because Valgrind essentially, as I understand it, preloads dynamic libraries which replace all of these calls and then adds its tracking on top. So you can do this for development on your desktop. It's not exactly suitable for machines or devices which are resource constrained, and it's not available for Zephyr or RTOS at all. So you can use this to get a little bit of glimpse into what might be going on, but it's not a solution for putting it onto your device. Yeah, Thomas, exactly. So I've used it on ARM9s back in the day. It can help you with some things, but it's definitely not something that you can use for prolonged periods of time. So, as you already said, sanitizers. And here's one which you are probably already using if you know me, but you probably have never heard about it. So Fortify Source. Fortify Source is basically a macro that you enable, which is supported by the libc and toolchain combination. You can enable it just by passing O2, so it requires optimization to kick in, so the compiler actually knows a little bit about what's going on, and by enabling the Fortify Source macro. It cannot detect everything, but it can help you. That's what I'm saying. And it incurs close to zero cost. Why is that? And let's look a little bit at how its effects are. This is on godbolt.org. So you can, we will also play around with it a little bit. I've basically entered the very same source code here. If I just build it and I throw it into GCC, nothing bad happens, and that's just like not super happy. See, these three parts. I've got the buffer, I override it, and the compiler just says, you're good to go. Scary. So if I add O2 and fortified source, what happens? The compiler tells me, hey, dude, you're doing something bad here. Please check what's going on. This is part one. It also adds a little bit of runtime checking, but I'd like to focus on build time checking here. Yeah, and as Michael said, boom. I like it if things go boom as quick as possible, basically during build time, so I don't even ship stuff, right? And that's basically everything I really wanted to explain. So let's look at it in the code for 1 or 2 minutes, and then let's also look at it in Yocto, and then you hopefully just say, yeah, I feel good about doing it the right way. So let's do this away. So this is a little bit extended, just the very same code. I've got the buffer with 16. I want to print into it with a limit of 64 maximum. And the problem is the compiler just happily builds it. And when it runs, it says, too bad, segfault. And we can now try and beat it into 45 source. And as I said, this already tells us, okay, there's something bad going on. Check your code. We could make it happy again by, let's say, what might happen here. See, no overflow detected. It all passes through. If you're dealing with compiler flags and crazy stuff like this, I always encourage you to head over to the Compiler Explorer by Matt Gottbold, because you can check out everything super easy, not having to care about your local tool chain, variety of compilers, blah 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 blah. You can really just type the code, compile, run, and be happy with it. First part. Second part, let me take that one away from you again and find my Yocto build. Where is it? Share screen. Dip, 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 dip. Yay. Here we are. Right. No, not yet. At the stage. Here we go again. So in this case, I've built a small demo, basically exactly the same. Let's just use string copy. I'll show you the source in a second. So Fortify, this is the second small part about Fortify source, the runtime detection. It tells us, hey, there's something going on, and the application aborts before something bad can happen. There's also the no Fortify. See, now it goes on, and a later stage of kernel protections, stack smashing detection kicks in. Why was I noodling so much about this being relevant in terms of Yocto? Let's take a small look at the Yocto defaults. In Yocto, there's this thing that's called securityflags.conf. And unless you are trying to trick your way out of it, this is actually enabled by default. So if you're doing bad stuff, default Yocto build will already enable O2 and fortify source. This is the magic here. It checks the optimization level, and if the optimization level is high enough, then fortify source is automatically enabled. Cool, right? So thanks to whomever of the Yocto people who inserted in back then, and that's also the reason why the demo that I had to create for this session, in order to make it go boom. So let's look at the source code for a second. It's really just what I showed you in Godbolt. See, create a buffer, write something to it. That's just oversized. That's why if you want to reach such a thing in Yocto, then you actually have to beat the recipe to disable the security flags for your build. See, this is the default. Everything is already using fortify source, and only if you beat it hard enough using an override for the flags, then you can actually provoke malicious behavior. What am I trying to tell you here? As always, do not reinvent the wheel and trust the error messages that your compiler gives you. Demo 1, I also showed you Yocto, obviously. As I said, this cannot be emphasized much enough. I mean, many of the people who listen to me are experienced developers. Trust your compiler. It's very rare that it gives you a false positive for no good reason. It might be confused because you're doing something crazy occasionally. But in that case, treat the warning as an indication that you're doing something crazy. Read the warnings, really try to understand what's going on where, and use sane defaults. Don't homebrew everything from a makefile, blah, 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 blah. I mean, Meson, for example, is also said to have very good and sane defaults. Use them. Do not think you know better. It's very rare. If you diverge from defaults, make sure you know why you do it and also document it, so people who come after you know why it is there. As I said, this does not directly apply to memory-safe languages as Rust or Go, but again, there is still a lot of C code out there and freshly written, and this is the fun part about this. It also works on real-time OSs or Zephyr or whatever. It's just a compiler and C library thing. It does not rely on Linux or Windows or whatever. This can be used everywhere. Here's a little bit of more information on it directly from the man pages, because it is in the GCC itself. Red Hat has provided a more in-depth tutorial for you, and I found it worth mentioning how Valgrind does its memory checking, because, as I said, it's slow. You can't use it on the device, but it's a tool you definitely want to know about. What will we be talking about next time? I don't know yet, because I will be at Embedded World. Embedded World matches this time slot of the second Thursday each month this time, and so I don't want to keep you waiting. I'm gonna report live from Embedded World, and there will be definitely something which helps you make your connected devices more secure. I just don't know yet what I will find at the show. And that's basically it already. Hit subscribe if you don't want to miss out on the next session, and drop comments below. Whether you've got questions about what we covered today, ideas for future episodes, I always love to hear from you. If you're ready to implement professional OTA updates in your own projects, of course, check out Mender.io. The links are in the description, and hopefully see you in the next episode. See you at Embedded World. See you around wherever you are.